Morning everyone. Yeah, very good morning. Shall we begin the session? Yes, today's topic is memory and the clocking. That is, what are the various memory that is available, that is registers, primary memory, main memory, and how to use the clocking, or what is the main clock, or to use this one that is used with the memory and the clocking that is used with the combination circuit that do not share anything, that do not store any information. So let's start or wait. Yes, let's begin with the sequential circuits. What is sequential circuits? In which we have to give the input and that provides the output. That means if there are two inputs, then the output are 4. Why? Because 2 by 2 is 4. So whatever the input we are taking out, that is multiplied or that takes the power of the 2. Now, first one is there are two classes of the memory devices. One is the clock register, that is simply a register that stores the individual bits or the words, and the signal control the loading of the registers with its value as the input. And the next is random access memories, or the simple the memories that stores multiple words using an address to select which word should be read or written. And the examples of the random access memory or the memories includes virtual memory system of a processor, where a combination of the hardware and the software makes it appear to a processor that it can access any word with a large area space. So whatever the area space that is available, that is used with the large area space register files, where the register's identifier will be used as address. For example, when we talk about the IA32, Y86 processor, that will use with the 8 program registers, that is EAX, ECX, and so on. Now, when we talk about the registers that are one of the fastest memory, and it is used in the input and the output wars, that is used with the machine level programming. Registers also present or represent a small collection of the addressable words in the CPU, where the addresses consist of the register IDs that are generally stored in the register files, although we will see that the hardware can sometimes pass a word that is directly from one instruction to another to avoid the delay of the first writing and then reading the register files. Whatever the file that is available, that is used with the two classes. One is the hardware registers, one is a program register. When we talk about the hardware register, all the concepts, everything that is available is done with the hardware. That means everything. What are the hardware issues we are using? Then program registers, whatever the program we are considering, whatever the tools we are considering, that is a program registers. Now this gives a more detailed view of the hardware registers and how it operates, and for most of the time the register remains in a fixed state, that generating an output equal to the current state, and the signal propagates through the combination logic circuit. For example, if I'm talking about the normal circuit, there is a AND gate, for example, that is considered, and there are two inputs, so there are 4 output that is available, like this one. This is one of the register file. There's a val variable or the val1 source A, so val B source B, A B. This is the register file. Then W, then val W, destination W. This is the write port. This register file has two read ports, namely the A and the B, one write port, that is the W. So there are two read ports and one write port, and this is used with the multi-ported random access memory that also allows read and the write operation to take place simultaneously. And when we talk about the register file, that is diagram, the circuit can read the values of two program registers and also updates the state of a third one. And each port has an address input that indicates which program register should be selected, whether it is using the data value, data output, input that gives a value for that program registers. And the addresses are the register identifiers, whatever we are using the register identifier that is taken out with the using encoding that is used with the two read ports, namely the source A, that is SRC-A, SRC-B, that is used for the source A and the source B, as I said, and the data outputs, that is a val A, val B, value A, value B, and the write port, that is the destination W, and the data input, that is a val W, short for the value W. And the register file is not a combination circuit, since it has an internal storage. In our implementation, however, the data can be read from the register files as if it were a collection of the combination logic, having the addresses as input and the data as output. When either source A, source B is set to the some register ID, then after some delay, the value stored in the corresponding program register will appear on either val A or the val B. And for example, when we talk about the source A to the 3, that will cause the value of the program register EBX to be read out, and this value will appear on as an output, that is a val A. And the writing of words to the register files is controlled by the clock signal in a manner similar to the loading of the values in a clocked registers. Now this is the one of the register. One is error, then read, write, data memory, data out, address, data in, clock. And this memory has a single address input and the data input for writing, data output for reading. Like the register file we are using, so the reading from the memory also gives the output in a manner that is similar to the combination logic. And if you provide an address or the address to the input, output that carries a 0 signal or the 1 signal. Now next is sequential Y86 implementation. Now this memory is used for the writing and the data output for reading, and like the register files reading from memory, whatever the memory we are taking out, that operates in a manner that is similar to the logic circuit. Now next is sequential Y86 implementation, that is used with the components to implement a Y86 processor. And as a first step we are using we describe a processor known as the SEO or SEQ, that is sequential processor, and on each clock cycle SEQ performs all the steps that is required to process a complete instruction, whatever the instruction that we are taking out, whatever the data that we are taking out. And that also requires a long cycle time. However, so use the clock rate that will be unacceptably low. And the main purpose is developing the SEQ is to provide a first step towards the ultimate goal of implementing an efficient and pipeline, whatever the main routine, whatever the data that is required for the efficient pipeline processes. The next is organizing the processing into the stages. What are the various stages that is used? This is the main thing. So first step is fetch. We have to fetch the instruction. We have to read the bytes of an instruction. We have to extract the bytes of an instruction using the PC, that is a program counter, as a memory address. So whatever the memory address we are using, that is covered from the PC. And from the instruction, it extracts the 2-byte portion or the 4-bit portion of the instruction specifier byte, that is referred as the I code or the instruction code, and the ifun, that is the instruction function, that possibly fetches a register specifier byte given one or both the register operand specifiers, and also possible fetches a 4-byte constraint word val C, and also computes to the address of the instruction following the current one in a sequential order, whatever the sequential order that is available, that is used with this. And this VIP also equals the value of the PC that plus the length of the fetched instruction. So one is the fetch, that means extracting the data, then decode, that takes the 2 operand from the register files within the val A and the val B, then execute. So one is the fetch, then decode, then execute. So in the execute stage, the ALU either performs the operation specified by the instruction, computes the effective address of the memory reference, or increment or decrement the stack pointer. So we reference the resulting value as a val E, and the condition codes are possibly set for the jump instruction for the data, and the stage tests are equally or that is taken out with the condition code, branching code given by the ifun to see whether or not the data will be accessed or data will be taken out. So one is a fetch, then decode, then executes, then next one is a memory. So the memory stage may write the data to the memory or may read the data from the memory. We also refer the value read as the val M or the value M. Then write back. So this stage writes up to the 2 registers or the 2 results to the register files. Then PC update. So the PC is set to the address of the next instruction. That loops infinitely, or it go infinitely performing the stages. And in our simple or the simplified implementation, the processor will store whenever any execution occurs that executes a hold or the invalid instruction. That is used to write an invalid address, give the complete design. Processor would enter an exception handling mode and begin executing special code that is determined by the type of the exception. And the main challenge is to arrange the computing results for each of the instruction set, whatever the instruction set that is given, that is available with this, that is used to take the format that is used with the y86 instructions. So whenever we are taking out, so that will be used with the instruction that will be used or taken out with the data for the hardware that do not perform these evaluation in a strict sequential orders. This is the computation in a sequential implementation of the y86 instruction. And this figure that shows the processing required, whatever the processing required for the instruction type OP1, integer, and the logical operations RR move 1, IR move 1, immediate processing. Now, whenever we are using, so it will take the processing, it will take the instruction, follows a general pattern that is listed above. And in the case of the first stage, we do not require a constant word, so VAIP is computed as a PC plus 2. So it will take as the PC plus 2 during the decode stage, during the code stage that do not require a constant word. So VAIP is computed as PC plus 2, and during the decode stage, we read both the operands, both the operators, that is computed to the ALU in the execute stage, along with the function specified for the hyphen. For example, when we talk about the instructions SUB1 EAX EDX, that is supposed to compute the R register EDX minus register EAX. And nothing happens in the memory stage for these instructions. But when we talk about the val E, that is written to register RB in the write back stage. And the PC is set to val P to complete the instruction execution. Now, next is tracing the execution of the sub1 instruction. So executing an RR move 1 instruction proceeds much like an arithmetic operation, and we do not need to fetch the second register operand. However, we are using the first instruction, that is ALU is input or is set to 0, giving the val E equals to val A, that is written at the register file. This is an example of how the processing will be taken out by the RR move 1 or IR move 1. This is the fetch, then decode, then execute, then memory, then write back, then PC update. Now next is what is the hardware structures. So just read out these things, then we will start with the hardware structures. Okay. Next part is the SEQ hardware structure that is used with the hardware units. What are the various hardware units? That includes the input device, output device, memory devices that we can touch, that is tangible in nature in simple terms. That is SEQ hardware units that associate with the various stages. For example, if I'm talking about the input device, there are multiple input devices. We are talking about the keyboard, mouse, scanner. These are the input devices, right? And the hardware units are associated with the different processing stages. Same stages, one is the fetch, that means extraction of the data, extraction of the bytes, then memory, then write back, then PC, decode. So these are the various instructions that is used. So one is a fetch, one is a decode, one is a execute, one is a memory, one is a write back. And this is used as these are used as two read ports A and B, which has register values, val A and the val B that can be read simultaneously. And the execution stage uses the ALU unit for different purpose according to the instruction type, that performs a specified operation that serves as an adder to compute an incremented or decremented stack pointer, to compute an effective address, or simply to pass one of its input by the or we can say divide the input of the by the output by the 0. And the condition code register also holds the 3 condition codes bits. New value for the condition code that are computed by the ALU, and when executing a jump instruction, then branch signal C and D is computed based on the condition codes and also the jump type. The data memory reads or writes a word of memory when executing a memory instructions, and the instruction and the data memories access the same memory location but for different purpose. Then register file has to write the ports. Port E is used to write the values computed by the ALU, and port M is used to write the read the data values from the data memory. And then SEQ is used to implement the hardware selection, software selection that have a multiple hardware design. So when is hardware units are shown as light blue boxes, and the control logic blocks are drawn as a gray round rectangles. Then wire names are indicated in a white box. Worldwide data connections are shown in as a medium lines. Then bytes and narrower data connections are shown as a thin lines. The single byte connections are shown as a dotted lines. So all these computations have a various line that have a property that each line represents each computation in a specific value. This is the PC, then memory, then execute. That includes the ALU, ALU-A, ALU-B, then decode the instruction, then PC increment. That have multiple values, val A, source B, val B. Then SEQ timings with the use with the implementation of the combination logic and the two forms of the memory devices, clocks registers and the random access memory. And this clocking and the memory is all that is required to control the sequencing of the activities in our processor, that is used with the hardware achievement, that is used with the same effect as is used with the sequential execution of the assignment that is shown in the tables. Update that actually occurs simultaneously when the clock rises to the next cycle. And each of the diagram labeled 1 through 4 shows the 4 state elements, then plus the combination logic plus the connection among the various or the state elements. Then this is the stage implementation. One is a fetch, that is the same. These are the various names, values and the meaning. Code for the NOP instruction, code for the halt instruction, RR move instructions. This is used with the iname error that generated when the instruction address is out of the bound. Then decodes and write back stages. Then memory stage, what is the memory stage, how the data will be captured, how the data will be showing together. The next one is the general principle of the pipelinings.